Okay, we are on notes number 19 today, and we're about halfway through chapter 4. So we've been doing some things with quadratic functions, graphing them, quadratic expressions, factoring them, and we've started solving quadratic equations. And we also looked at simplifying radicals because we need to do that when we solve some quadratic equations. And so we're going to move on from here, and today our topic is called complex numbers. But we're going to start with solving a couple equations of the form that we were looking at in our last lesson. So suppose we have to solve the equation x squared minus 5 equals 3. So if we use the method of solving by square rooting, we're going to start by adding 5 to both sides and then square root both sides. So we get x equals plus or minus square root 8. And then we simplify the radical and we have x equals plus or minus 2 square root 2. So that was pretty straightforward. Now we have a similar looking one. So let's solve the equation x squared plus 11 equals 3. So we'll start by subtracting 11 from both sides and then square root both sides. So we have x equals plus or minus the square root of negative 8. So at this point, it's possible that from your previous experience you would just stop because the square root of negative 8 is not a real number. You can't take the square root of a negative, is what you've been taught. However, mathematicians don't really like to say we've reached a dead end and we stop. Instead, what mathematicians like to do is create something new, define something new. So let's make a new definition. Suppose you could have a number that was the square root of a negative. Let's call it something. And that's where the idea of imaginary numbers comes in, and then from there, complex numbers. So this is kind of to be continued. So here's how we define an imaginary number. We define the square root of negative 1 as I, lowercase I, and we define I squared as negative 1. I is called the imaginary unit. So these are the definitions that you want to commit to memory. And every time you see an I squared, you want to change it to negative 1. And every time you see the square root of a negative, you're going to change the notation to involve I. So if you saw the square root of negative r, so r is a positive, so this would be like the square root of negative 5, you would write it as I square root 5. So let's do this example. If we have the square root of negative 12, we're going to write it as I times the square root of 12. So this is an imaginary number. And then we can simplify the square root of 12 like we would simplify other square roots. Square root 12 is 2 square root 3. And so we're actually going to write this as 2i square root 3. So in a way, when you have I involved in an expression, it kind of gets treated as if it was a variable. So if you had 2x, you would write 2x, you wouldn't write x2. So it's kind of like that. We write 2i, we don't write I2. Okay, so now back to the idea of solving the equations, kind of like that one that I said to be continued on. If we had this equation, we could isolate x squared, so we're going to start by subtracting 18 from both sides. 2x squared equals negative 90, and then divide both sides by 2, so x squared equals negative 45, and then square root both sides, so we have x equals plus or minus the square root of negative 45. So we're not going to say no solution, we're now going to say, oh hey, we have imaginary solutions. Let's simplify them. First of all, we have plus or minus I times square root 45, and then you can simplify the square root of 45. It's 3 square root 5, so it's plus or minus 3i square root 5. Okay, now let's give this one a try, and you might just want to pause, try it yourself, and then resume and see how you did. So we're going to add 7 to both sides, and that gives us 3x squared equals negative 24. Divide both sides by 3, so x squared equals negative 8. Square root, so x equals plus or minus square root negative 8. And then simplify that radical, x equals plus or minus I square root 8, so x equals plus or minus 2I square root 2. Now, you might be wondering, if we have numbers that we're calling imaginary, what's the point? Like, are they useful? Do they exist anywhere? And so this slide just shows you some of the fields that actually use imaginary numbers. It's kind of mind-blowing, but maybe the term imaginary is misleading to make you think that it's not real or not useful. These are some areas where imaginary numbers actually do come into the mathematics. We don't spend a whole lot of time on the applications. There's only a tiny, tiny bit in your book. It's about a circuit, actually. The way the electricity flows around a circuit has to do with imaginary numbers. So there are a couple of examples of that in your book. So we know about real numbers. Now we know about imaginary numbers. Put them together and we have the set of complex numbers. So a complex number in standard form is written as a plus bi, or you might see a minus bi. The point is that the first term, a, that represents the real part, and the second term, bi, represents the imaginary part. So a and b are real numbers. Now, what if a is 0? If a is 0, all you have is bi, so that could be something like 3i, 4i, I square root 2, etc. So that would be purely imaginary, but still complex. What if b is 0? So if b is 0, you would have numbers like 5 and 2 and negative 12 and pi and so on, any real number a. So those are just purely real, but they're still complex, because complex numbers are now at the top of our tree diagram. Complex numbers divide into real numbers and imaginary numbers. And then we know that real numbers divide into rational numbers and irrational numbers, etc., etc. Remember from the first day of school. However, a lot of times you will hear people, and probably you'll hear me as well, kind of misusing the vocabulary. Sometimes we say imaginary when we're really talking about complex. Sometimes we just interchange those two words. So we're not going to be super strict about that. I just want you to know that that is a possibility. For the second half of the lesson, we're going to look at what you can do with imaginary numbers. In other words, how do you operate with them mathematically? How do you add them, subtract them, multiply them, divide them, all that kind of stuff? Kind of like when you learned about fractions in elementary school. You learned how to add them, subtract them, multiply them, divide them, what they were, how to reduce them. When you learned about any kind of number, you learned what you can do with it. How do you operate on it? So let's start with adding and subtracting. So here I have two complex numbers, 12 minus 11i and negative 8 plus 3i, and to add them is just to add the like terms. So add the real parts, 12 and negative 8, and we get 4, and add the imaginary parts, negative 11i and 3i, and that's minus 8i, and then to write it in standard form means you have your real part and then your imaginary part. So 4 minus 8i. Here we're subtracting, same idea. Don't forget to distribute the negative sign. So subtract the real parts, 15 minus 24, and that's negative 9. And subtract the imaginary parts, negative 9i minus negative 9i is 0i. We're not going to write it like that, we'll just write it as negative 9. We don't have to write plus 0i. Okay, here we see a purely real number, a complex number with both real and imaginary parts, and then we see a purely imaginary number. It really doesn't matter. Remember to distribute the negative and just combine like terms. So 35 minus 13 is 22. And then negative 4i plus I would be negative 3i. So 22 minus 3i. One more for practice. Give this a try, and then you can check your answer. 3 minus 8 is negative 5. 7i minus negative 2i is positive 9i. So negative 5 plus 9i. Okay. Next we're going to look at multiplying. And we'll write our answer in standard form. So this is just like working with variables and using the distributive property. We have negative 5i, and we're going to multiply it by 8, and we're going to multiply it by negative 9i. So negative 5i times 8 is negative 40i, and then negative 5i times negative 9i would be positive 45i squared. So we have a little bit of work to do to simplify this. First of all, what is I squared? Remind me? What's the definition of I squared? That's right, negative 1. So you substitute that in. And then we realize that the second term here is just negative 45. That's the real part, that goes first. Negative 45 minus 40i. And that's our answer. Okay, let's multiply these. You can pause, give it a try, and then see how you did. So we're using the FOIL method, so negative 8 times 4 is negative 32. Negative 8 times negative 7i is positive 56i. 2i times 4 is positive 8i. And 2i times negative 7i is negative 14i squared. So let's combine the like terms, the I terms. And then let's also change I squared to negative 1, which is going to mean we have plus 14. So negative 32 plus 14 is negative 18. So we have negative 18 plus 64i. Okay. Now this is a special one because you see one with a plus and one with a minus. Have you seen that before? Think about when we were simplifying radicals and we had things like 3 plus square root 2 and 3 minus square root 2. Do you remember what we called those? And do you remember what special thing happens when you multiply them? So we call these conjugates. And when you multiply them, the insides and outsides cancel. So the same thing is going to happen with imaginary conjugates, or non-real, I guess complex conjugates we should call it. When you multiply the first, you get 9. When you multiply the outsides, you get negative 3i. When you multiply the insides, you get positive 3i. See how the insides and outsides are going to cancel? And when you multiply the last, you get minus I squared. So really, if you realize that you're multiplying complex conjugates, all you need is the first and the last, because the inside and outside cancel. Remember, I squared is negative 1, so this is actually 9 plus 1, so this is 10. So keep this in mind, that multiplying complex conjugates gives you just a real number. That's real. So if you ever need something that, say, doesn't have an imaginary number on the bottom, just like with radicals, if you don't want to have a radical on the bottom, then you use conjugates. So that brings us to the idea of division. Remember how with matrices there was no matrix division, but instead we had to use an inverse? Well, in a way there's no complex number division. Instead we have to use a conjugate. So let me show you what that's going to look like. So let's say we have this ratio of one complex number over another. You could think of it as one complex number divided by the other. And so what we have to do is multiply by a special form of 1. What special form of 1 do you suppose we're going to pick? What could we multiply by so that the denominator simplifies greatly? The conjugate of the denominator. So the conjugate of the denominator is 3 plus 2i. So let's multiply the top and bottom by that. That's going to be our special form of 1. I'm going to multiply the denominators first. So the first, 3 times 3, that's 9. Insides and outsides cancel. And the last, minus 4i squared. And then for the numerators, we're going to FOIL. So the first is 15. The outside, plus 10i. The inside, plus 6i. And the last, plus 4i squared. Now let's change both of our I squareds to negative 1. And we have 15 minus 4, we have 11, plus 10i plus 6i, 16i, over 9 plus 4, 13. Okay, so notice there's no longer a imaginary number on the bottom, but we still need to write this in standard form. And standard form has a separate real part and imaginary part separated with plus or minus. So we'll just separate this into two fractions. 11 13ths, that's our A, that's our real part. And then 16 13ths I, 16 13ths is our B, and 16 13ths I is our imaginary part. So there it is in standard form. So let's try another one. Maybe pause and try this and then compare. So I'm going to multiply by what? The conjugate of the denominator, 5 plus I, over itself for my special form of 1. So when multiplying the denominators, we're going to have 25 minus I squared. And when multiplying the numerators, the first is going to be 15, the outside 3i, the inside 20i, and the last 4i squared. Change the I squareds to -1. And we have 11, oh, another 11, lucky number today. We have 11 plus 23i over 25 plus 1 is 26. So we'll just write this as 11 26 plus 23 26i.